So today I'm going to present to you a method of control which happens to be very efficient. Efficient in terms of performance in the time domain and the frequency domain. I'll go gradually and I'll try to give an intuitive approach to it, although the hard mathematics will be sent separately for anyone who wants, no problem. Well, so this method that I suggest offers elegant solutions for unstable and invertible plans, okay? Which means zeros in right half plane, we have still problems with them. No, we don't have a solution for that. We have tried it experimentally on the levitation system with great success, on the drone also with success, for a satellite antenna controller, how to orient a satellite antenna from one place to the other, from one angle to the other very fast, was done successfully, but by simulation only. For some logistic reasons, we didn't do it on the field. We tried it also on multivariable systems, and we achieved decentralized control, which means we have diagonal controllers, and we achieve decentralized control. That means one input controls one output, just like if the closed loop was diagonal. We have also developed very simple, intuitive, interactive methods which basically allow the tuning of the parameters. And we recently went to adaptive control. We chose L1 adaptive control, which is considered to be one of the most advanced methods. And we try to improve on it, which with some success simulation-wise. Again, the list is not over. I just received this week a company of robotics from France would like me to try it on robustness of some problems they have, and they like the elegance of the solution. So things are open. There is also many possibilities around the corner. So this result, what's important to remember is that it's fast and robust control. That means you get an excellent time response and an excellent frequency response in terms of phase margin, in terms of gain margin, in terms of you're very happy with that. And I'll take you through it until L1 adaptive control, which is an improvement on L1. So first, I'll just recall some basic performance objectives. Then I introduce the controller, okay? And then I'll go to adaptive control. Remember, just a unity feedback system. P is the plant, C is the controller, R the input, and we have the perturbations D1, D2, D3. And when we look at this, at least on a CISO system, we have 4 transmissions that we can that you have to tune in order to improve. That means what you would like to have is Y equals R. That means direct link, or closed loop equals 1. And for the others, we'd like to attenuate the transmission to D1, D2, D3 as much as possible. Now, the big controller is based on sensitivity. The framework is a unity feedback system, although we can tune around it. It's based also on the integral sensitivity trade-off, which I'll present in a second, and the relations that go with it. And on constraints, I'm going to impose from the start some sensitivity bounds on low frequency and at high frequencies. As for the closed loop, I'd like it to be obviously stable, but also as close as possible to unity. The phase margin, I'll follow on Strom by taking ideal phase margin of 66, 67 degrees, more or less. At the same time, I'm going to pay attention to 2 factors. Number one, the U of S, that means the plant input, I'm going to limit the plant input to avoid saturation. And number 2, I'm going also to put a limit on C of S, which is the compensator. That means when I'm going to compare existing simulations or existing systems with my simulations, I'll use the same kind of gain and I'll use the same kind of saturation input so that we can compare apple with apples. So the feedback system, basically T plus S equal 1, T being the closed loop as the sensitivity. we can see that t plus s equals 1 is ideal. So good tracking means t equals 1, from which follows that s equals to 0. But as we know, for causal system are strictly proper. That means that infinite frequency, t of infinity is 0. So it's impossible to get 1 at all frequencies and at 0 at all frequencies. So what we're going to do is simply divide our system into, we have here the low frequency. I'm going to establish a limit omega-1 per frequency, and another limit, up to omega-1, and a limit at high frequencies. More practically, at low frequencies, I'm going to say that my sensitivity should be smaller than epsilon, and at all frequency, smaller than m. Why is it important to limit the sensitivity at all frequencies? Is understood by this diagram, a log sensitivity integral. Normally, when you have 1 over 1 plus Cp, when C's gain increases, then 1 over 1 plus Cp decreases, and we get lower sensitivity. But there is a waterbed effect in the sense that the blue area is equal to the green area. So if you keep increasing the gain, lowering the sensitivity at low frequencies, you might simply increase the sensitivity here, and maybe you get some resonant frequency that you'll wake up and end up in big problems. That's why what I'm saying now, I'm going to limit this at low frequency. At high frequency, I'm going to put an upper bound here. This upper bound is going to give me the same area, but the area is going to be extended at higher frequencies. Why? Because today we have sensors which have very high frequencies. We have DSP, which allows us to take care of a higher bandwidth. So if we take this green area and flatten it more on the higher frequencies, it's possible to have good sensitivity. That means a big blue area with a lower bound, and at the same time having the bound at all frequencies. So those considerations, as I said, are made easier by the new sensors and by DSP. And then there's a magic property to this. It's called the quasilinear property. Okay, the quasilinear property is very important here, and I explain in a moment what it is. What I mean by quasilinear, that means that the gain and the poles are related somehow, are interdependent. So a little recall, I'm on the Nyquist plane, and this is the closed loop gains, we call the M circles. That means the modulus of the closed loop. And obviously, M equal 1 is the ideal. That means if my Nyquist could stick to this line, to this red line here, that passes from -0.5, I would be a winner. So I'm going to take something very simple. What would be the ideal Nyquist? It should be something which respects the fact that the sensitivity is smaller than epsilon at low frequency. What are low frequencies? High gain. Low frequencies, I'm outside this circle. This is called the sensitivity circle, because if you take the, let's say, G of S, 1 plus G of S, and 1 over this, smaller than epsilon, you get simply you have to be outside the green circle at low frequencies and outside the blue circle at all frequencies. Those are very simple geometric considerations. So if we could have something like that and then stick as much to the -0.5 as I could and then go back, would be fantastic. Or I could go around the blue circle as many times as there's any right half-plane poles. What is this quasilinear property? Normally, I'm showing this in a Nichols plane. When you increase the gain, obviously the Nichols graph goes up, and then it gets closer to the instability, critical point. That means 0 dB, 180 degrees, and then the system starts to oscillate and then blow up eventually. The whole idea is by making this pole and gain dependent. When I increase the gain, the pole is modified, so I always keep the good gain margin, phase margin. And it so happens by doing so, when I'm increasing the gain, look what happens to the time response. It gets better and better and better. While normally the time response gets worse and worse and worse, here I'm increasing the gain and I'm getting some result which is really not intuitive, but nevertheless true. So to explain intuitively, I'm going to suppose that P of S is stable and invertible. That means no right-hand poles, no right plane zeros. And I'm going to build a compensator P minus 1 P. That means basically I'm left with J. J is me, it's me. J is what I'm building. And I'm building a low frequency with high gain here, but as I told you, for low frequencies. This element here is another filter, low-pass filter at higher frequencies, where this frequency is dependent on this gain. Okay, there's a dependency. And at the same time, I make sure that the power K makes sure that this is strictly proper. That means that C of S itself is strictly proper, so that everything's fine. So what I'm left with, J2, and J2 is simply a phase circuit. That means the phase circuit is for the intermediate frequencies, and it has a very important role to play later on for the fine-tuning. Obviously, this is one thing. I can add a pre-filter, I can add a predictive filter, but I'll stick to this scenario for now. In case I have something unstable, well, I'm going to decompose my system into stable and invertible and unstable. I'm going to invert the invertible part, and for the rest, I'm going to build a new function that behaves like P of S at high frequencies, or getting close to it at high frequencies, so that I'm applying this algorithm directly. That's going to be my algorithm for my loop gain, and the proof is complicated, but nevertheless it works beautifully. I'll show you this. Oh my God. Oh, I have a problem when I open my second. I have to open my okay. When I have a double screen, I cannot open my okay.
Do you want to do the simulation?
No, no, it's okay. I'm there. I'm there.
Okay, you're there. Fine.
Okay. So those are, I'm going to work here with tuning factors. Example M, the sensitivity at all frequency. You see the red line here is my top sensitivity. And you can see it's the M circle, it's the red one that you see here. It's there. So I'm staying always tangent to it. And low frequency is the epsilon one. You can see the green should improve, should change the green. Those are different factors. I can simply play on my parameters until I get the sensitivity I want and the transmittance I want. And what you see here is U is the input to the plant, which means I'm going to adjust so I do not exceed the, you see here, my U max stays under a certain value. Okay. So this is adjusting, and we keep adjusting the parameters. And in fact, this can be done very easily. As you can see here, the line that you see here, the blue line, is the line of -1/2, at which my Nyquist is basically here. So what we have here, we have a place, obviously, my Nyquist goes to 0, goes to the origin at high frequencies, but J2, intermediate frequencies, is tuned in here, which means with J2, I use phase circuits in order to make this line closer to this vertical line, and it works. Okay, so I'm going to put that down. I'll go back to my system. So example, I imagine all of you saw the YouTube. I don't have to show it again. The YouTube is about levitation. It was done in McGill in the lab, where we compared the levitation system. We have a ball. We want to ask the ball to go from one step to another. And we have 3 or 4 master theses where people spend days and nights trying to tune the PIDs to get the best response. And we applied our algorithm, and our algorithm has shown much better response. That means rise time equals settling time and no overshoot. And when we compare by simulation everything with H infinity, TH2, we have advantages. So when I'm looking at my gain, look here, when I'm increasing the gain, I'm getting closer and closer to the ideal. And I'm increasing the gain, so I have one unsettlement because levitation is not a stable system. I need one unsettlement, but by increasing the gain, I'm making this line, but here, which is -1/2 here, I'm getting closer and closer to it by increasing the gain. So it looks too nice, but believe me that when you work with the geometric solution, you apply it, it works beautifully and things are tuned. And this is the videos. What I'll spare you the video because I imagine everybody has saw it before. Is it the case? Yeah. Would you like to see the video?
Absolutely. Please go ahead.
Oh, okay, I'm sorry. Okay, I have 2 videos to show you. So this, I hope it's the English one. Let's see. One second.
We have developed a method that increases the speed, stability, and precision of a control system by an order of magnitude compared to today's leading technologies. As you will see in the video, the impact of this method is meaningful enough to be observable to the naked eye, but is even more impressive when measured with a high degree of precision. We will demonstrate the method using a very simple magnetic levitation control system, but the applications are significantly broad. In general, systems react faster when the gain is increased. However, a gain increase to a high enough extent in certain systems can lead to oscillatory behavior and instability. With this algorithm, we get improved time response when we increase the gain while maintaining stability and robustness.
This new algorithm takes advantage of new sensors, which are much more precise, have higher resolution, higher bandwidth, as well as digital signal processing units, which work much faster. Our compensator is shown here in this diagram. We invert the invertible parts of the compensator and add some corrections, as well as 3 filters. J1 acts on low frequencies, and J3 acts on high frequencies. And those 2 filters guarantee the realizability, the stability, the robustness of the system, while G2FS acts mainly on the time response, reducing the settling time and the rise time without affecting really robustness margins. That's the strength of the algorithm as it is now.
So to test our magnetic levitation device, we have a diagram here that describes the components of the system. And mostly what we want to do is to levitate this spherical metallic ball here with using an electromagnet that will lift the ball as we're putting current through it. So what we have here is the magnetic levitation device, and the ball is magnetically levitated right now, and it's under the control of a PID controller, which is proportional integral derivative. What we see is that the ball is steady at a position, and then we change the set point so that the ball can move up a notch by about 1 millimeter, as we see here. The response time is not great, and there is a little bit of overshoot, which is something that we will correct with the new control.
We apply now a new control algorithm on the levitation system, and we're going to give some step inputs and check how the ball is reacting on the vertical plane. And as you can see, there's almost no oscillation when we go from one step to the other. If we look at the time response and zoom on it, we can see that there's almost no overshoot, no static error, and in less than 60 milliseconds, we get a nice response. Note also that the rise time and the settling time are equal. If we do compare our compensator to a PID compensator, which has been optimized after many, many trials, we observe the following. Number one, the overshoot is quite important. Static error is small, but the settling time is quite big, 650 milliseconds. Therefore, our compensator performs much better. To validate qualitatively the robustness of the system, we're going to hang different objects, different shapes, different weights, and check the result without modifying the compensator. This is the result. The algorithm can be applied to any system, and we apply it to a hard disk. What we would like to do is control the arm of the hard disk and make it vary from one position to another the faster possible. So we take our hard disk model, apply our algorithm, and compare the solution to the other solutions that do exist. As you can see here, with PID, we get 63 milliseconds. With H-infinity, 1.5 milliseconds, with H-infinity control. With algorithm, we get 0.27 milliseconds. In fact, comparing simulation with simulation, we see that our algorithm is much more interesting.
For more information on this patented technology, please contact either Aligo, a company specialized in the marketing of university inventions, or directly to the research professor.
Okay. So we continue. I'll get to the multivariable case. I'm taking a case where I have an unstable system, which is analytically invertible. And I'm going to assume only that it's ultimately diagonally dominant. And for that, I'm going to show I can get decentralized control. I sent the article to Automatica. It has been refused many times because there's a theorem by Davidson from 1983 saying that it's impossible to have decentralized control in diagonal control for unstable systems. But again, people didn't pay attention to the fact that I'm demanding simply that at high frequencies, the system becomes diagonally dominant. That changes the whole thing. So the paper has been accepted, then refused, back and forth. It's very hard to go against the grain, but you'll see in a second how everything is perfect. So what is this decentralized control? Decentralized control because the sensitivity is equal to t-1. So if you can multivariable, if you minimize the sensitivity at low frequencies, what happens is this difference becomes small. That in t gets closer and closer to 1. That means you get diagonal transmission. And what we do, I'm going to take this system here. Right? This system, I have the invert, and I'm using my algorithm directly. Also assuming that at high frequencies, it becomes diagonally dominant. Diagonal dominance means basically that the transmission on the diagonal are more important than the sum of the transmissions on the rows or the columns of a system. And this is what I'm getting. You see, you have here the closed loop of the multivariable system. It's a 2x2 system. T11 is 0 dB. T22 is 0 dB, but the coupling T12 and T21 are 40 and 60 dB lower, which means I'm getting really diagonal transmission in here. Let's look now at the time domain. At the time domain, this is what happened here. Again, this is the Y11, and this is the Y21. That means that I'm getting also a time domain which is perfectly diagonal. The transmission of is an ideal transmission at both outputs. If I'm applying this to a drone, quadrupter, again, quadrupter, I'm going to use two feedbacks, one for the moments, one for translations. And what I'm getting is something like that. The whole idea is to take this drone and make it glued to this vertical pole as much as possible. So we did many trials in the same meteorological conditions. And this is what's happening with the PID of the manufacturer. It's kind of hard to stick to the pole. Try again. Anyway, this is what the manufacturer proposes. I'll go now to my algorithm when I apply it to the drone. Okay, so let's try to stick to the pole. Beautiful. And when I'm going to compare the fluctuations on the horizontal plane, I'm getting the H2 controller gives me a lot of fluctuations around on the horizontal plane. H infinity, the blue, and you can see here that my algorithm gives you a very good answer. So in a way, it's a good decentralized control. We tried it also on to control satellite antenna. We have a model of satellite antenna that we received, and what we have to do is basically build velocity feedback and a position feedback in order to get improved. And without a big effort, because we can still add, as I said, pre-filters, we can still add predictive filtering and so on. The overshoot goes from 30 to 0.06, selecting time to 4 to 1.5. Again, for the position feedback, from 15 overshoot to 0.12, settling time from 3.5 to 0.45, which means if you have a satellite and you want to orient it from one angle to the other, but fast and stick with it and get and lock on the target, you can do it much faster with no oscillations, no overshoot, no nothing. Let me go now to L1 adaptive control. So adaptive control is good for systems which have parametric variations. which are more or less unpredictable, and we're trying to track the system and compare it to a known model and try to minimize the difference. And we do that with a few methods. So we're going to take those methods and simply try to insert our controller, our B control. We call it B control for now because we know how to call it, inside, and have a solution. It might be interesting to try it. So in controller, adaptive control, we have what they call direct MRAC, where you have a reference model and you want your system with all the perturbations, you would like it to be to emulate this reference model. And the difference is set in a feedback. And as you can see here, it's what we call the MIT gain. Although MIT gain, and there's some, how to say, some reservations about its theory, but many people use MIT gain successfully for basic designs. But for sophisticated design, I would go to a more sophisticated Lyapunov function. This is the indirect MAC, where I do the same thing, but this time I have a state observer, and the difference is going to be fed back. And I'm going to. The problem I have with those two methods, direct and indirect, is that when I increase the gain up, what's happening? My phase margin decreases. And that's a problem. So if I want a fast adaptation, a good tracking, I have a problem. My phase margin gets smaller and smaller. So the whole idea is to add here a special filter. A special filter here that's going to have an interesting effect. It's going to decouple the feedback from the adaptation. More precisely, this is my filter. It's a low-pass filter. The rest is the regular mechanism, but only the low-pass here. So my feedback is not perturbed by all the small fluctuations, while the adaptive mechanisms still take them into considerations. Doing that, we get interesting results. Meanwhile, you can see that this time, when you increase the gain, then you have a better phase margin, which is great. In fact, the whole design of the F1 planes have been restarted completely by introducing the L1 method, because the adaptation showed to be very, very interesting. So now, how to introduce this new controller, how to introduce it to my architecture? There's many ways to do it. I mean, I'll show the simplest one is to take a setup of, this is my system, my L1 controller, and I consider it as a plant, and I am trying to use my compensator for this stabilized plant. It's possible to do it, and those are the parameters I'm choosing, and let's see the results. First of all, the time response output to input. Okay, those are, I used this example with gain of 2000, 2000, because I took exactly the same parameters that are used in the literature, and I'm comparing the same with the same. And you can see here that the time, look at the scale here, it's 0.5, here it's 0.05. So my time response is improved tremendously. And again, I can still improve with pre-filtering and predictive filtering. That's one thing. Number two, let's see the effect of input noise on the output and of output noise on the output. This is the L1 response, and this is the BL1 response. So this one basically disappeared, and this one is attenuated substantially. So there's many possible architecture. I can introduce B controller here on the real plant, and then compare it to another plant got by observation, and do the feedback and apply the L1. I can also compare my system, my closed system, to this one. This one is the ideal system. It's just like a step, but not really a step. It's a step that I can really materialize because g of s is the function I have built my system with. And what we're getting, generally speaking, is that we have an excellent tracking by using B-control. Again, I used only one architecture so far to check the adaptation, but it works. Look here now. Remember that sigma was the input perturbation and n was the output perturbation. The whole idea here is to take the y, the output, or x that will be before the noise, and try to make sure that y to r is 1, okay? And y to sigma is small, and y to n is small, same for u, and so on. So there's certain transmissions I would like to attenuate, and some would like to keep close to 1. If I would like to, I use Masson's formula to get transmissions, and this is what I'm getting. I'm getting here the transmission output to external noise, output to input noise, here input of the plant to external noise, and so on. I take all the possibilities, and I have also at the end here my output x to r, u to r. I would like them to be good, and those are not affected. The feedback loop is not affected by C of S. Remember, because the adaptation loop was somehow disconnected from the stability loop. So already we have shown we have some improvement, but there's something else we can do. How to use this filter? So far, in the literature, they have suggested this, mostly this filter, very simple filter. Some have chosen this one. And not what we're doing here is introduce some new filters, which somehow try to reconstruct the profile that we have in our B controller. So by doing that, we're getting to, second. This is what you're getting. So those are the parameters of the filters. What you see here are the transmission. Remember, y to n, y to sigma, and so on. And I would like all of them to be within 1. That means we'd like to have attenuation. So I'm having here, you see, I can adjust the filters until they get all in a circle less than 1. I can play with some other factors. Some are, this is simply here, omega box. So what I'm saying here, when I'm using this sliding rule here, I can play until I get the transmissions I want. And that's easier than trying a filter and a second one and a third one. Here, by simply moving this ruler here, I am able to have this filter. There's more to it. I mean, I could continue, for instance, let me give you another example. Okay. The design, the students love it because today, even a PID can be tuned, even a PID can be tuned with a slide. So this is, this is my system. And look, let me take off this, enable this. This is my M, my closed loop. I want like to be vertical if possible. Here I can see my J2. Remember, J2 was the intermediate frequencies. Intermediate frequencies allow me to work mostly on this region. And I can play with, I can play with the parameters I have until I get something. This, I tried only one phase circuit around here, but I could add more phase circuits in order to have better improvement here. what you see here, if I'm going to, you see here a circle which is 1. In a circle which is 1, the blue that you can see here is T. That means you would like T is a closed loop to be as close to 1 as possible on the maximum number of frequencies to have good tracking. What you see here in orange is C over C max. That means if I'm saying my gain should be smaller than a certain value, well, I normalize my gain, and while I'm playing with the parameters, I make sure that my gain does not get out of the circle of 1. That means that I'm respecting the conditions on the game. Okay. So this is for fine-tuning of the time response. Okay. There is also here with the pre-filter, we can also play with the pre-filter and also try to adjust it to have better, you see, that we can play with it and get very good results until we finalize on this plane. We can finalize the frequency performance, and we can also present here the time response. And with that, simply, I think I finished and I'm ready for questions.